So today's topic, conditional probability and bias rule. This is very popular topic in many fields, and this bias rule, what we call bias rule, is used in different environments. So people from medicine, from physics, from sociology, from economics, they're using this bias rule. Why? Because it's a very powerful tool to calculate probabilities of some events when you know at least something about those events. And the underlying concept of this bias rule is a conditional probability. So first of all, we need to understand what is this conditional probability, and then we will try to see what is bias rule, how this works, and we will see several examples. So let's start right away from the concept of conditional probability. So we know what is the probability of an event. Now, what is a conditional probability? We have two events, event A and event B. And a conditional probability of an event A, given that event B has occurred, is equal to this ratio. So we call this probability of A given B is equal to the probability that A and B occur together divided by the probability that B occurs. And some kind of terminology that this BA given B, so this vertical line, is read probability of A given B. So what is important here that event B occurs, and we know that event B occurs, and after that event A must occur. So this is the conditional probability. So the condition for event A to occur is the occurrence of a condition B, of an event B. So let's see an example, and let's see how this formula works, how to apply this. So a simple example, we roll a die and we have two events. So one event observe 1. Another event observe an odd number. So right away, what is the unconditional probability of event A? This is very simple. Just simple probability of event A. Guys, come on. It's very simple. You have a die and
I think
yeah.
1 out of 6.
1
Oh,
over
it
6.
does?
Yes, it's simple. You observe 1 over 6 is a probability of event A without conditions. What is the probability of event B? Observe an odd number. So odd number is a number which is not divided by 2.
Is
1
0.5.
0.5, 1 over 2, 1/2. Yes, that's perfect. So you know these unconditional probabilities. So now, look, that's exactly what you said. Omega is the sample space, 1, 2, 3, 4, 5, 6. Event A consists of only one element, it's 1. Event B consists of 3 elements, 1, 3, and 5. Great. So now, look, suppose after rolling a die, someone says that there is an odd number. So you don't see the exact number on a die, but someone tells you that there is an odd number. Look what happens. So the question is, what is the probability that there is 1? That's exactly a probability of event A given that event B occurred. So once again, you don't see what's there, but somebody tells you additional information. Somebody tells you, well, there is event B occurred. Now, this is exactly a conditional probability. How should we calculate this probability? So now your sample space is not omega, but B. Why? Because you know that there is an odd number, and you know that out of odd numbers there are 3 possibilities, 1, 3, and 5. So you restrict your sample space from 6 elements to 3 elements. And now it is simple to calculate what is the probability of A out of B, or A given B. It's 1/3, right? So I divide one event by 3 events. So if all outcomes are equally likely, then this conditional probability is 1/3. So this is an idea of conditional probability. Once again, if you don't know this additional information, then probability of A is 1/6. But when I'm given some additional piece of information, when I know that there is an odd number, I restrict my sample space from 6 elements to 3 elements, and therefore this additional information gives me a chance to update my probability. And the updated probability is going to be 1/3. So now let's go back to that formula from the previous slide. So how should we apply this formula in order to calculate the same result, 1/3? Probability of B, you correctly said that this is 1/2 or 3/6. Probability of A and B together is 1/6, right? So A intersection B. Why? Because A intersection B is 1, and probability of 1 out of 6 elements is 1/6. So this means that events A and B occur together. So now I take this probability of A intersection B and divide this by probability of B, and I have the same 1/3. So this is an important concept. Why in economics, for example, why do we want to use this concept of conditional probability? So suppose we want to know what is the probability that tomorrow the stock price will increase. If it's unconditional probability, then kind of it might be, let's say, 50% or 55% or 60%, so it depends on the nature of the stock. But now, if you know something in addition, so for example, you know that today this company introduced a new product, and given this additional information, you can update your belief about future probability, about the probability of future stock price increasing, and maybe this probability will be 70%. So that's how we use this concept of conditional probability in practice. One particular example. You will see more in this lecture. So now, another way how to work with these conditional probabilities, and particularly I like this tool because it gives you, let's say, the whole understanding of what's going on, is a contingency table. So it's a simple way to understand the conditional probability. Look, I built this table for the previous example, and I calculate how many elements do I have on under each intersection of two events. So in columns I have odd and even numbers, B and not B, and total. And in rows I have 1 and not 1, so A and not A, and also total. So how many odd and even numbers in total I have? 3 and 3 is here. So how many ones and not ones I have? 1 and 5, it's here. So look, now if I want to calculate probability of A, I'm taking 1 and I divide this by 6. If I want to know what is the probability of an odd number, probability of B, I'm taking 3 and divide this by 3. And inside this table, these 4 numbers, inside this table I have the number of elements that possess both criteria. So how many odd ones do I have? I have one. So it's A and B together. How many A and not B do I have? 0. So there are no ones which are even numbers, right? So how many not ones in odd numbers do I have? 2. It's like 3 and 5, right? 2 numbers. How many even numbers that are not 1 do I have? 3, like 2, 4, and 6. And these numbers inside, they are the elements in this set A intersection B. So now, what is the probability of A intersection B? I'm taking this one and I divide this by 6. What is the probability of B? For example, I'm taking this total 3 and I divide this by this total 6. What is the probability that of one given B? Look, now total is different. When we are speaking about conditional probability, I'm not taking the total of all events, but I'm taking the subtotal of this particular column. I know that if there is an odd number, so this second column is not valid, so I don't need this second column. I only need the first one. And my first column becomes a sample space. And I know that the total number of elements in the first column is 3. That's why I need to take 1 and divide this by 3. And that's it. And I'm done with the calculation of this conditional probability. So this is a simple way to calculate conditional probability, but kind of don't be relaxed. You need to understand also this formula, this previous one, because in some cases still the formal approach to this calculation is needed. But whenever you can, use these contingency tables and they will save your life and they will give you the clear picture of what's going on. So any questions about the conditional probability and so the meaning of this conditional probability? Do you understand what is that? Okay, so we will move to other examples and probably we will have some questions. So now there is a multiplication law, which is the consequence of this definition of a conditional probability. So we have two events, A and B, and probability of B is non-zero. Then probability of A and B together equals to probability of A given B times probability of B. Look, this part is something that you already know. If you remember from the previous lecture, the multiplication principle, how to calculate the probability that two events occurred together. We have this, look, so first of all, probability of B. So we need to know that what is the probability that B has occurred. And then, if B has occurred, I need to calculate the probability that A occurred. Look, for example, let's say event A is to randomly select a boy from a group of students. Event B is to randomly select, let's say, a brunette from a group of students. So we know that there are brunette girls, brunette boys, so it's B and not B, and A is boys and girls, A and not A, right? So how to calculate the probability that I will select a brunette boy from a student group? So first of all, this is the probability that I will select a brunette person. And given that I selected brunette person, I need to select a boy out of this group. Why this? Because you remember that if I will multiply probability of brunette times unconditional probability of boys, it's not correct, because I have an intersection of these two events and I cannot multiply them straightforward. I need to do this only in a following way. Or I can reverse this relationship. I can say, well, this is also a probability of selecting boy first, and then out of boys, I will multiply this by the probability that out of them, I selected a brunette. Right? So this is a reversal procedure. Actually, both of them give me a probability of A intersection B. And this relationship opens a huge field of possibilities for us, of kind of manipulations over this conditional probability. Because look, if I know something about the conditional probability of A given B, I can tell what is the conditional probability of B given A. I can reverse this procedure based on this multiplication law. This multiplication law is very, very important thing in the whole topic. So now, an example. An urn contains 3 red balls and 1 blue ball. 2 balls are selected without replacement. What is the probability that they are both red? Try to calculate this yourself. Try to think about this and what is the result.
Is it 1/6?
We will see. At least we have one answer, 1/6. Guys, why many people are still without cameras?
1/12.
Okay, we have another option, 1/12.
Also think 1/12.
Okay. We have 2 people for 1/12, 1 person for 1/6. Nice. So one option is 1/6, another option is 1/12. So we have some answers in chat. So any other ideas? Anybody else? Okay, so let's see. So first of all, at the first step, so let's denote R1 and R2, the events that the red ball is drawn on the first trial and on the second trial, right? So first we need to calculate the probability of R1. Probability that I will draw a red ball, I will take a red ball on the first draw. So what is this probability? What is the probability to take the red ball on the first step?
1/4.
Not exactly. So how many red
Yeah.
balls do we have?
It's 3/4.
It's 3/4.
Yes.
It's 3/4 because we have 4 balls, and the event red ball consists of 3 elements, right? So I have 3 balls there. So, okay, so this is the from multiplication law. How should I proceed in order to calculate the probability of R1 and R2, meaning that I want to get 2 balls, 2 red balls. So probability of R1 is 3/4. This is clear, right? Because I'm taking one of 3 red balls out of 4 in total. But then look, next probability is a conditional probability, because if I take out 1 red ball, now my sample decreases. I have less red balls and I have less balls in total in the urn. So there are 2 red balls and 1 blue ball left. What is the conditional probability to draw red ball on the second step?
2/3.
2/3, yes. And in total,
Mm.
I have 3/4 multiplied by 2/3. And I have what? I have 2/4 or 1/2. So probability to take 2 balls, 2 red balls on 2 consequent draws is 1/2. So now those who gave answers 1/6, 1/12, do you understand what has happened and why do we have 1/2? So once again, look, maybe let me illustrate it. So on the first draw, we have 3 red balls, so 1 blue and 3 red. Okay, orange. 1, 2, and 3. So on the first draw, I have what? I have 3/4 probability to take a red ball. And on the second draw, when 1 is removed, when I don't have this red ball, so this is a conditional probability now, because this is a probability to take a red ball on the second step, conditional on the fact that in the first draw I already removed 1 red ball. So now it's 2/3. And now I need to multiply these 2 probabilities based on the multiplication principle, because I want to have red ball on the first move and red ball on the second move, right? Any questions about it?
No question. It's clear.
Okay, good. So let's move. So now we have something that is called the law of total probability. So this might seem a bit complex, but actually, once again, the logic is very clear. So let's say we have n events denoted as B, and union of these events B is the whole sample space. So remember, so here in this example, events B were odd and even numbers. So this is B1, this is B2, and their union is a whole sample space, either odd or even numbers in this example. That's what we are talking about. So these events B1 and B2, their union gives a whole sample space, and what is the most important, that they do not have an intersection. So BI and BJ are disjoint events. So odd and even numbers are disjoint events, for example. You cannot have the intersection of odd and even numbers. This is the empty set. So probabilities of each event is non-negative and non-zero. And then look, for any event A, probability of A equals to the sum of these products. Probability of BI times probability of A given BI, where I changes from 1 to n. So for example, look, if you remember that first case about about rolling a die. So probability of an odd number is 1 over 2. Probability of having 1 given an odd number, it's 1 over 3, right? So 1 over 3 times 1 over 2 gives us 1 over 6. Now, probability of an even number, this is 1 over 2. Probability of 1 out of even numbers, it's 0. So I add 1 over 6 plus 0, and this is the probability of event A to draw 1. And here is some picture, so probably it will give you an idea so how this rule works. Look, we have 3 events, B1, B2, and B3. So those are these white areas. So B1 is this area, B2 is this area in the center, B3 is this area to the right. So their union gives us the whole sample space, the whole rectangle here. Now we have the whole event A. This whole event A is here, this gray ellipse inside. And look, in order to calculate probability of event A, we need to sum these small pieces of this event. So this part of event A, this part of event A, and this part of event A. And we know how to calculate the intersection of event A and B1, event A and B2, event A and B3. In order to calculate this intersection, we should apply this multiplication law. Conditional probability multiplied by this probability of event B. That's exactly here. This is the probability of an intersection A and BI. B1, B2, and B3. So this is the visual illustration of this law of total probability. And so we will have an example to apply this law of total probability. So an urn contains 3 red balls and 1 blue ball, and as in the previous example, 2 balls are selected without replacement. What is the probability that a red ball is selected on the second draw? So try to think yourself, try to apply this law of total probability, and then we will discuss. So basically we know the answer, right? Because we did it. No.
I think
Actually no, because we have now different cases. Okay, so go on, please. We have one particular case when red ball on the first place, on the first draw was taken, and we know what is the probability to have a red ball on the second draw. But now we have an additional possibility. What if a blue ball in the first draw was taken?
Isn't
Then
it
what?
also 2 over 3?
Yes, but we have another probability of a blue ball taken on the first draw. And well, no, wait. If a blue ball on the first draw was taken, then the probability of a red ball on the second draw is different. So be careful with this logic. So any ideas, any particular answers?
uh, 3 or 4, right?
Okay, 3 over 4, that's one answer.
Yes, it's 3 over 4.
Okay, second answer, 3 over 4. Any other opinions? Now let's get this back. So basically, look, on the first step, we have two options, right? Two possibilities. There are two possible outcomes. So a red ball was drawn, this one, and the second, a blue ball was drawn. Right? So on the first step, we have two possibilities. So what are the probabilities of each outcome? What is the probability that the red ball was drawn? This is a probability of R1. So you know this.
3 or 4.
3 or 4, true. 3 or 4. Okay, so what is the probability of not R1, that the blue ball was drawn? So
1 of 4.
1 or 4, yes. So this is the first step. Now look, if we have the first outcome, so then we have on the second step, so given that R1 occurred, we have this. So now we are interested in this particular outcome, so that the red ball was drawn on the second step. given that on the first step it was also red ball. So what is this probability? We have 3 balls together, 2 of them are red, so we know that 2 over 3 is this conditional probability, right? But another option is this. So given that R2 occurred, sorry, not R2, but R1C occurred. So not R1 occurred. Then we have this. Then blue ball is not there, and we have only 3 red balls. So now what is the probability to draw a red ball if on the first draw you have taken a blue ball out? What is the probability to draw a red ball here? Conditional probability.
Is 3 over 3 is 1.
What?
Yes, it's 1. It's
One?
1. Of course. Of course. Now look, I have 2 ways how to draw a red ball on the second step. One way after taking red ball on the first step. Another way is to take a red ball after the blue ball on the first step, right? So I need to sum these two, the probabilities of these 2 ways. So now my total probability of R2 consists of 2 parts. So this is the union of these 2, let's say, of these 2 branches. So one is the probability of R2 given R1 multiplied by the probability of R1, of course. Probability of R1. And plus another way how I can get red ball on the second step is to get a blue ball on the first step, which is this, right? So I sum these 2 probabilities, and finally I have the total probability of having a red ball on the second step. So what's here? It's 3 over 4. That's 1 over 4. Wait, no. 2 over 3, this probability, multiplied by 3 over 4. So this is the probability that I will take a red ball on the first step and the red ball on the second step. Plus probability that I will take blue ball on the first step, 1 over 4, times probability that I will have red ball on the second step. I need to lay down all possible ways how I will arrive at that second event. I can get red ball on the second step, either having red ball on the first step or having a blue ball on the first step. And this gives me what? So this is 1 over 2 plus 1 over 4. In total I have 3 over 4. So those who told 3 over 4 were correct. So now I explained you all steps how to arrive at this result. And here we have the same. So we have these probabilities on the first step. Then we have conditional probability of R2 given R1, and then conditional probability of R2 given B1. And in total we have 3 over 4. Same answer. Any questions about the law of total probability?
Not really, like a question, but I just didn't get how do we come to the calculations of the answer?
Once again, how do we what?
Why do we calculate the answer like that?
Aha.
I just didn't get the task. I didn't get the example, I guess.
Okay, so look, you want to know, so just in general, you want to know what is the probability to get a red ball on the second draw, unconditional probability. No conditions there, just you want to know if you have this urn with 3 red balls and 1 blue ball, what is the probability to get a red ball on the second step. So now you try to break up this event into two pieces. So one piece, how you will arrive to the red ball on the second step. You need to take the red ball on the first step, and then from the leftovers you will also take the red ball on the second step. Why? Because the probability of red ball on the second step depends on what you have on the first step. This is one way, and that's how we calculated this first part. But also, you have another opportunity to get a red ball on the second step. On the first step, you needed to draw a blue ball. And this adds, let's say, another piece of this total event of having red ball on the second step, which is here. So whenever you take the blue ball on the first step, on the second step you will definitely have a red ball, and then you add these two probabilities, because we have two ways how to arrive at this final outcome. Not sure how was this clear or not. Let me give you another example, maybe. Okay, let me give you another example. Just so what do we have here? Yeah, we have bias rule. Okay, so let me give you this. So maybe it would be better to understand the idea why are we doing this. So let's A is an event. Select, let's say, girl from a group of students. So therefore, AC is going to be select boy, right? Not A. So now, let's say B is an event. Select a brunette person from a group of students. And not B in some other color. Select not a brunette person from a group of students. So now let's see what do we have. For example, according to this, we know the following. We know that, for example, probability to select girl is, well, let's say 60%. And now I also know the following. I know that out of, so something like, let me show this in words, and then we will write this formally. We know that, let's say, 70% of girls are brunette. Just, I mean, I'm taking some voluntary numbers, so it doesn't mean that this is true. And we know that, let's say, 40% of boys are also brunette. So now, what is the probability to select a brunette person from a group of students? That's something that we are doing in the previous example. So look, how can I select a brunette person? So I can select a brunette person either from boys or from girls. So what is the probability to select a brunette boy? So this is the probability of, so formally now in this language of probabilities, this is a probability of B given not A, right? Given not a girl. I want to select, so no, wait. This is here. So probability of having brunette out of boys. And this is the probability to have a brunette out of girls. So now, what is the probability to select a brunette boy? This is the probability of, so kind of formally, it's probability of B and, meaning intersection and AC. From the multiplication law, we know that this is a probability of brunette given that this is the boy, multiplied by a probability that a person is boy. Okay? So what is this? This is 0.4, 40% of boys are brunette, and probability to draw a boy out of the group of students, so this is also 0.4 from here, right? So here probability of AC is 0.4. Okay, so now this is what? This is 0.16. So this is one way how I can draw a brunette person. 16% that the brunette person is going to be a boy. Now, what is the probability to select a brunette girl? This is B intersection A, and this is the conditional probability of B given A times the probability of A. So now I know that 70% of girls are brunette, and out of all students I have 60% of girls. So the result is 0.42. So now I have probability to select a brunette boy 0.16, probability to select a brunette girl 0.42. Now, what is the probability to select brunette boy or brunette girl? Because I want to have a brunette person out of a student's group. So this is the total probability. This is the probability of B, which is first part 0.16 plus second part 0.42, and in total I have 0.58. This is the total probability to select a brunette person out of a group of people. Let me give you another representation of this case just to understand it better. That contingency table that I told you about. So let's try to make this contingency table, and let's try to see how to work with this contingency table in this case. Look, we have boys, girls, total. We have brunette, not brunette, total. So what do we know? We know that here must be 1. So the probability to select some person with some hair color is 1. What else do we know? We know that there are 40% of boys. We know that there are 60% of girls. What do we want to know? We want to know this. We want to know what is here. What is the probability? What is the, let's say, the share of brunette people in the whole population? What do we know? Look, we know that 70% of girls are brunette, B given A. It means that, look, out of this 40%, 70% is here and 30% is here. So how should I calculate the probability inside this cell? It's 0.7 multiplied by 0.4. Look, 70% in this column, 70% out of 40%. That's what we did here. Wait, no, wait. I'm wrong. 70% of girls. Sorry. 70% of girls. It's here. 0.7 out of 0.6. I'm calculating this intersection of brunette and girls. And that's what we have, 0.42. So I know also that there are 40% of boys. So 40 here and 60 here, 60% of boys, right? So I multiply 0.4 by 0.4 and I have 0.16. So now it's simple to establish all other cells here. Basically, nothing is difficult, right? I can calculate that 0.6, 60% of not brunette boys, gives me how much? 24% in total. So not brunette boys, probability is 24%. So not brunette girls, the probability is 0.3 times 0.6, which is 0.18. Let me give you some. So this 0.4 is from here. This 0.4 is from here. So these two numbers, so this and this. Wait, why? This and these are taken from the initial setup, right? So I know that 40% of boys are brunette, so therefore 60% are not brunette, and this as well. So the 70% here and 30% here is given to me from, well, I don't know, from some research, from some observations. So, but they are given from the side. And now in total I can calculate it here. So 0.16 plus 0.42, which gives me 0.58. And I'm able to calculate with the help of this table basically what is the probability to have not brunette people. It's 0.42, right? Just simply 1 minus 0.58. So I know this. Knowing this, I need to reconstruct what is here. And with the help of this, I can calculate what is the unconditional probability here. Basically, that's the way how we operate it. Okay, now it is better.
Yes, much better, I guess, with this example.
Maybe with balls it's not that clear, but with this, when you have two different characteristics of a person, maybe probably better. Okay, so let's move to the last concept in this lecture. So now, when we know this initial idea of a conditional probability, so remember, conditional probability is the probability A given B, which is the fraction of their intersection divided by the probability that B has occurred. This is one building block. Another building block is the multiplication law and the law of total probability. So we need these two pieces. And now look, now I am taking this and I am able to plug this into the definition of a conditional probability, and I have something that is called a bias rule. So let's start from the end of this formula. So first of all, we have an event A, and we have disjoint events B1 to Bn that form the whole sample space, and their probabilities are positive, so non-zero. So let's start from the end. What is this? This is the definition of a conditional probability, right? So probability of Bj given A is simply probability of their intersection divided by probability of A. Now, here in the numerator, I apply the multiplication law. Look, what is the probability of A intersection B? This is the probability of A given Bj multiplied by the probability of Bj. So this is multiplication principle here in the numerator. What do I have in the denominator? In the denominator, I have the law of total probability. Total probability of A is the sum of these products, probability of A given Bi times probability of Bi. And this is called the bias rule. So we basically used two things or three things that we studied during this lecture. And we came up with something that is widely used in many different fields. So now I will give you two examples of this bias rule application. I hope that they're going to be interesting and they're going to be illustrative enough to understand the concept of bias rule. So let's start. First example, a polygraph test or lie detector tests. So they often used to kind of test employees or prospective employees in some sensitive positions, whether the person is going to lie or not. Of course, we know that these machines are not fully precise, and there are possibly some mistakes. So let plus, so not a letter, just a sign plus, denote the event that the polygraph reading is positive, indicating that the subject is lying. So you are testing the person, And the machine says you that, well, this person lies. But of course, it might be a mistake. So let T denote the event that the subject is telling the truth. So now let's L denote the event that the subject is lying. Now, according to studies of polygraph reliability, probability that the polygraph will show you a positive result given that the person lies is 88%. So it means that 12% that the person is liar and the machine will not reveal this, right? So here 12% that when person lies, machine is not able to recognize this. And also probability of a negative decision when the person tells you truth is 86%. So which means that in 14% of the cases, the person tells you truth, but the machine thinks that the person lies, and the machine tells you that the person is liar. I hope you understand the whole concept, right? So the machine can give you positive or negative result, and the person can tell you truth or can lie. And we have conditional probabilities of this machine reliability. So sometimes when a person, so basically, ideally, we want to have this conditional probability to be 1, right? So machine tells you a positive result when the person lies. But occasionally machines are not perfect, so that's why it's only 88% when the person lies that the machine says you or shows you a positive result. And 86% of the cases machine tells you negative result when the person tells truth. So I think you are able now to build this contingency table somehow, or probably not yet. So now, suppose that polygraphs are routinely administered to screen employees for security reasons, and on particular questions, the vast majority of subjects has no reason to lie, so that probability to tell truth is 99% and probability to lie is 1%. So this is the setup of our task. So kind of unconditional probability that the person tells truth is 99%. And unconditional probability that the person is liar, 1%. Now, the question is, so the most interesting part of the story. A subject produces a positive response on the polygraph. So the polygraph says that the person is a liar. What is the probability that the polygraph is incorrect and she is in fact telling the truth? What is the probability that given positive response of a polygraph, a person tells us truth? Try to think about it for a minute. We need to have these numbers, I guess. So basically, what you need to calculate? You need to calculate probability of T given plus. That's what you need to calculate. Probability of T given plus. Try to think, try to apply this concept.
So T given plus it is P. So what will be first in the bracket?
Probability of T given plus. So okay, let me rewrite the whole story here in order to have it. So what do we know? We know probability of plus given L is 0.88. So we know that probability of minus given L from here is 0.12. So these are just, if a person lies, the polygraph either tells you positive result or negative result, right? So that's why in total you have 1 here. So then probability of plus given truth is 0.14. Probability of plus minus given truth is 0.86. We know that the probability that the person tells truth is 99%. Probability that the person lies is 0.1%. We need to know probability that the person tells truth if the polygraph shows us a positive response here.
I think we should 0.88 multiply 0.01 and plus 0.
Okay, try to
and
calculate
0.
and try to give us the answer, and then we
Yes,
will...
I calculate the answer is 0.1474.
17. Okay. That's one answer. Basically, we need to think in the following way. What do we know about the conditional probability? So conditional probability is calculated as the unconditional probability of, so in the denominator we must find what is the probability that the polygraph gives us a positive response, right? So it must be here. And in the numerator we must find the joint probability of person telling truth and the polygraph shows us a positive response. So now in the denominator you must apply the total probability.
No, I'm sorry. I said
and here you must apply multiplication.
I said 0.1474 is the total probability, and we must probability that the test was incorrect, so is computed has its 0.9403.
So 0.9403 is in the numerator, this joint probability.
Yes, the final answer.
The final answer is 0.8.
And 0.9403.
0.9403. Okay.
Yeah.
Anybody else has an answer? Look, try to think. If you think about the numerator, for the numerators, I think it's kind of not that difficult. So the multiplication law is a straightforward thing. What is the probability of t intersection plus? We need to find some conditional probability of either plus given t or t given plus. We basically have plus given t here, right? This is the first part of the story. And then the probability of plus given t. And you see that this is the reverse conditional probability here and here to what we want to calculate. Actually, that's how we can reverse this conditional probability, and that's what Bayes' rule did. Bayes' rule does. And we need to multiply this by what? We need to multiply this by the unconditional probability of a person telling truth. So what do we have here? 0.14 multiplied by 0.99. So this is the first step, the simple one. 0.14 times 0.99, 0.1386, 0.1386. Right? We have a numerator. Great. Now, we need to calculate the denominator. What is the denominator? What is the unconditional probability of a polygraph giving us a positive response? Now we need to carefully think about it. I can have a positive response in two possible ways. One possible way is that the person lies and I have a positive response. Another way that the person tells me truth and still polygraph gives me a positive response. So I need to sum over these two probabilities. So first of all, probability of positive response given the person lies multiplied by the probability that the person lies plus actually this plus this. So what's here? 0.88 multiplied by 0.01 plus this 0.1386. 0.88 times 0.01 plus 0.1386. So that's 0.1474. Okay, so now I can apply Bayes' rule because I have this 0.1386, 0.1474. The result is 0.1386, 0.9403. Yes, 0.9403. So basically, that's very interesting. Even if a polygraph shows that the person lies, there is a 94% chance that the person tells the truth. So kind of completely unreliable machine. So the machine gives you a signal that the person is liar, but 94% probability that this person tells you truth. Why is it so strange? Because of these small conditional probabilities of these two chances. If I increase the reliability of my machine, if I increase this percent from 88 to, let's say, 99, and this one as well, then I will have this conditional probability much lower. But even this small, it's like, it can be taken like, okay, 88% is quite reliable machine. But you see how it happens. Basically, in 94% of the cases, the machine responding that the person lies will be false. That's how we can apply this Bayes rule in practice to understand that even if the machine reports you something, there's probably a high chance that the machine is not correct. So here is a short way to multiply this. I will upload all these calculations on the Moodle page, so don't worry, you will see all of this. I just need to save it. to save it somewhere. Factor 4. Okay, so 95% of positive polygraph readings will be an error. Any questions about this, about bias rule and about its application? So now I will show you another kind of very, how to say, fresh example of an application of bias rule. This might be applied not to COVID-19, to anything, but once again, you need to understand carefully that there are some similarities with what we did before. So suppose we want to investigate the percentage of people infected by COVID-19 in a certain population. The events of interest are: a person is infected, I, and its complement, the person is not infected, N. So this is something like a person lies or tells truth, right? So the same story here: the person is infected, the person is not infected. So now we assume that 1% of population is infected, 99% is not. Just again, for simplicity. Now, the classification as to whether a person is infected or not is based upon a PCR test examination. You know this. So because tests are not perfect, they sometimes classify an infected person as one that is not infected. So NT, where NT means classified as not infected by a test. On the other hand, some tests might show you a positive result, IT, when the person is not infected. So the same story as for the polygraph. Sometimes when you are infected, test shows you negative result. Sometimes when you are not infected, test shows you positive result. This is an error of a test. So suppose that the error rates of misclassification are: probability that the test will be negative given that the person is infected is 4%. Probability that the person that the test is positive when person is not infected is 5%. And correct decisions are made in 96% and 95% of the cases. Completely similar story to the previous one. So guess what we want to calculate? So calculate the probability that the person taken at random is classified as infected by a test. So what is the probability that a random person will be classified as infected? So should I go back to these numbers? Okay.
Like we need to find a probability of IT.
Probability that the randomly person is classified as infected. So probability of IT, yes. Probability of IT, just unconditional probability that the test will show you a positive result. let me meanwhile to polygraph. Example about the COVID. What we have. So probability of I expected here. Now probability to show negative results even if the person is not infected. 5. Probability to show positive result even the person is not infected. Here probability to show infected when the person is infected. Not. Or now, first question, we are interested in this. So what is the probability that the test will show us the result that the person is infected? Any answers? Anybody calculated?
Maybe it's 0.0591, but I'm not sure.
0.0591. Okay, and anybody else? Just to check. So look, how we can arrive at this result, IT, either here, wait, there is something wrong, right, in my, yeah, so here must be this, not infected, given that the person is infected, yeah, so now it must be okay. How can we arrive to this result IT? Either person is infected and test is correctly showing this, or the person is not infected but test mistakenly reports this. So I need to find what is the probability of a person infected and test gives me a positive response, means this one, plus probability that the person is not infected and the test reports me positive result, this. So now I just must plug all the numbers. This times this plus this times this, 0.99. So let's see, just to save it time, yes, 0.0591. So this is almost 6% probability that the test will respond as positive. Which is okay. I mean, in 5% of the cases, the test will show a positive result, but only 1% of the population is infected. So now, high relative to the probability of an infected person. So once again, the probability that the person is infected when the test classified the person as infected is. So now we want to calculate this. Now we want to calculate that the person is infected given that the test shows us a positive result. Now we need to apply a bias rule, right? We know that here must be probability of the test positive, and here we must have probability that the person is infected and test gives us a positive result. So the fraction is 0.0591 here, and in the numerator we have this thing, right? We have this, which means this part, like this. And the result is, let me see, the result is 0.1624. 1624. So basically, if the test tells that the person is infected, there is only 16% chance that the person is really infected. 84% of the cases are false positive results, right? Why? Because once again, the reliability of the test is not that high. So the reliability of the test is just 96%. When person is infected, the test shows you a positive result. This is something that you need to take in your mind when working with all these things. When you rely on some tests, on some information that is not perfect, you need to understand that this test might produce a very low probability of a correct response, just because of this imprecision. So that's how bias rule is applied, and bias rule is applied also in some other fields. I hope that we will have some illustrations of this. Okay, so regarding the independence, we will finish this next time. Now let me stop here. Do you have any questions about bias rule? You will have some exercises and some tasks on the exercise session, so I hope that you will have a chance to better understand this topic and practically apply some of these concepts. Any questions?
Questions.
Okay, good. Then we will meet in 15 minutes for microeconomics. See you.